substitution monomolecular reaction. So in this, the example I'm taking is tertiary butyl bromide is going to react with a nucleophile to form tertiary butyl alcohol plus a bromide ion is generated as a byproduct. This reaction is known as SN1 reaction, where the tertiary butyl bromide reacts with a nucleophile to form tertiary butyl alcohol and a bromide ion. This reaction is known as nucleophilic substitution monomolecular reaction, which is denoted by SN1 reaction. And the kinetics of this reaction is kinetics. It follows first order kinetics. It follows first order kinetics. That rate of reaction depends upon the concentration of only one reactant, that is alkyl halide. Nucleophile reactor concentration is not important in this reaction, which is important in case of your SN2 reaction. But in case of SN1 reaction, the concentration of only one reactant, that is alkyl halide, is important. That's why this reaction follows first order kinetics. That means the rate of reaction depends upon the concentration of only one reactant, that is alkyl halide. Clear? This is what involved in this SN1 reaction. Coming to the mechanism. Mechanism, it is a two-step mechanism. In step 1, the tertiary butyl bromide where this bromine is electronegative, always it tries to pull the bond electron towards itself, thus creating delta minus delta plus, and the covalent bond is converted to polar bond. There is a weak bond which can be broken very easily. This is what the situation in there in this particular molecule. Because of this, further, this carbon is feeling deficit of electron, or it is losing an electron towards bromine, and further it is attached with 3 alkyl groups. These alkyl groups are electron releasing groups. They can donate electron towards this positively charged carbon which is deficit, thus nullifying the effect. So in doing so, the movement of the sigma electrons from this alkyl group to this carbon, movement of this sigma electron takes place. This movement of electrons will generate certain amount of energy. That energy is more enough to break a bond between carbon and bromine, where this particular tertiary butyl bromide undergoes heterolysis. Heterolysis means breaking of a bond, where there is a even distribution of bond electrons takes place. This process is known as heterolysis, where it breaks the bond, and thus what is formed is a carbocation is formed, plus a bromide ion is formed as a byproduct, and where this particular first step is a slow step, because the energy required to break a bond between carbon and bromine has to come within the same molecule. That is because of the movement of sigma electrons, and inductive effect takes place, and because of this inductive effect, the bond breaking between carbon and bromine takes place. Thus it undergoes heterolysis, where there is an uneven distribution of bond electron takes place. That bromine takes the bond electron and goes out as bromide ion, and ultimately what is formed is a carbocation is formed. Carbocation is formed. This carbocation is tertiary in nature, which is attached with 3 alkyl groups, which stabilizes this and makes the molecule more stable and highly reactive. So this immediately in the second step is going to combine with the nucleophile. Combines with the nucleophile to form tertiary butyl alcohol. To form tertiary butyl alcohol. This particular step is a fast step. So in mechanism, it is a two-step mechanism, where in first step, the tertiary butyl bromide, the bromine is electronegative. It always tries to pull the bond electron towards itself, thus creating delta minus over bromine and delta plus over carbon. And this carbon feels it's losing electrons to this bromine. And further, this effect can be nullified by the presence of 3 alkyl groups. They try to release electron towards this carbon. Thus, there is a moment of sigma electrons takes place, and which is called inductive effect. Because of inductive effect, it generates certain energy. That energy is more than enough to break a bond between carbon and bromine. So this tertiary butyl bromide in the first step undergoes hydrolysis, whereas the bond breaking takes place, where there is uneven distribution of bond electrons also happens. So because of that, this particular tertiary butyl bromide undergoes hydrolysis, where bromine comes out from the carbon taking bond electrons as a bromide ion, and ultimately what is formed is a carbocation is formed, and this carbocation is tertiary in nature, that is 3 alkyl groups are attached to it. That's why it is tertiary in nature, and because of this presence of 3 alkyl groups on this molecule, this carbocation becomes more stable, and hence it is more stable and it is highly reactive. But all this first step process is a slow process because it has to utilize its internal energy, and the energy which is required, which will come from the internal molecule, that is movement of sigma electrons because of the inductive effect. So because it has to use this internal energy, its own energy, so it takes place slowly. That's why this particular first step is a slow step. Once this carbocation is formed, which is stable and highly reactive, it immediately combines with a nucleophile in the second step. In the second step, there is a, because it is simple, nucleophile is rich in electron having a negative charge on it. Carbocation is deficit of electron having a positive charge on it. It's simple acid-base reaction takes place. So it immediately combines with the nucleophile to form tertiary butyl alcohol, and whereas it is a fast step. It immediately combines with the nucleophile to form tertiary butyl alcohol. Next one is stereochemistry part of this. Stereochemistry of SN1 reaction. So in this stereochemistry, we'll use that particular second step where there is a formation of tertiary, that is carbocation, tertiary cation. So the carbon is attached with 3 alkyl groups, and it has got a positive charge over that p orbital. So that p orbital is a dumbbell shape. It's a dumbbell shape. So one plane, one lobe line one plane, and another lobe line another plane. So that p orbital lie in 2 planes, right? And here, just according to the molecular orbital picture, it is like this, where dumbbell shape, one lobe lie in one plane, another lobe lie in another plane, and the positive charge, it may be present on this lobe or it may be present on this lobe. Both the chances are there. So the nucleophile which is going to attack this. So it may attach itself to this position or it may attach itself to this lobe, because it may be present on this lobe as well as this lobe. So the chances of the OH nucleophile attacking either on right side or left side is of 50-50. So this may be of 50%. This may be of 50%. It is like your crackjack biscuit, 50-50 metamamkine. So 50% of this, it may attach itself here, that is on right side, or 50% it may attach on left side. So ultimately, what is generated in this is a tertiary butyl alcohol is formed. But here, plus or minus tertiary butyl alcohol is formed. That is 50% of dextrorotatory, 50% of fluorotatory tertiary butyl alcohol is formed, and that is this particular mixture of 50% of dextrorotatory and 50% of fluorotatory is called as racemic mixture formation takes place. Racemic mixture formation takes place, and the process is called as racemization. The whole process is called as racemization. Racemization is a process wherein there is a formation of 50% of dextrorotatory, 50% of fluorotatory form is formed, or in other words, racemic mixture formation takes place. This process is called as racemization. So the stereochemistry of SN1 is a racemization process wherein there is a 50% of dextrorotatory and 50% of fluorotatory form is formed. That is, racemic mixture formation takes place. This is what the stereochemistry of SN1 reaction. Coming to the last point, which is reactivity. So in case of reactivity, the equation goes like this: tertiary butyl bromide, tertiary alkyl halide reacts faster than secondary. Secondary alkyl halide reacts faster than primary. Primary will react faster than methyl halide. This is what the reactivity for this SN1 reaction. Tertiary is going to react faster than secondary alkyl halide, and this secondary alkyl halide is going to react faster than primary. Primary is going to react faster than methyl halide. This is what the reactivity involved in this SN1 reaction. I'll just summarize all this SN1 reaction once again. SN1 is the nucleophilic substitution monomolecular reaction. It is simply denoted by SN1, S, capital N, and 1. It is denoted by this particular symbol, and where the definition for this is tertiary butyl bromide is going to react with a nucleophile OH to form hydroxy group to form tertiary butyl alcohol and a bromide ion. This reaction is known as nucleophilic substitution monomolecular reaction. Coming to the kinetics, it follows first order kinetics. That means the rate of reaction depends upon the concentration of only one reactant, that is alkyl halide. So the concentration of only one reactant, that is alkyl halide, is important in this reaction. That's why this reaction is called as first order kinetics. And because of all these parameters, it is called as SN1, nucleophilic substitution monomolecular reaction. Only one reactant is important, that is alkyl halide. Clear? Coming to the mechanism part of this, it is a two-step mechanism wherein in first step, the tertiary butyl bromide undergoes hydrolysis because that bromine is an electronegative atom. It always tries to pull the bond electron towards itself, and thus creating delta minus over bromine and delta plus over carbon, and the covalent bond is converted to polar bond, which is a weak bond which can be broken very easily. So it undergoes hydrolysis, and the energy required to break the bond between carbon and bromine comes within the same molecule because of the moment of sigma electrons, because that particular carbon, carbon is attached with further 3 alkyl groups. Those alkyl groups are electron releasing group. They always try to release electron towards that positively charged carbon, and they try to release electron sigma electrons, and because of this movement of sigma electrons, there is generation of energy takes place, and that energy which is generated there within the molecule is more than enough to break a bond between carbon and bromine. Thus, ultimately, in first step, by utilizing its own energy, it breaks the bond between carbon and bromine. Bromine comes out from the carbon taking bond electrons, and the process is called as hydrolysis. And thus, ultimately, what is generated is a carbocation is formed. And this carbocation further it is attached with 3 alkyl groups. That's why it is called as tertiary carbocation. And this tertiary carbocation, because all these 3 methyl groups are there, which are electron releasing groups, they stabilize the molecule more, and thus it becomes more stable molecule. And when it is more stable molecule, it is highly reactive. So that particular carbocation immediately combines with the nucleophile in the second step to form tertiary butyl alcohol. That's why that first step is a slow step, because it has to utilize its own energy and thus forms that first step carbocation. But immediately after the formation of that carbocation, which is more stable and highly reactive, it immediately combines in the second step with a nucleophile to form tertiary butyl alcohol, which is a fast step. So these are the 2 steps involved in this particular SN1 mechanism, nucleophilic substitution mechanism. Here, coming to the next point, which is stereochemistry of SN1 reaction. So to discuss with this stereochemistry, just go back to once again that step 1, that is formation of carbocation. So when we visualize this particular carbocation, tertiary carbocation, the molecular orbital picture which indicates like this, where that carbon which is having a positive charge with a p lobe empty, and it has been attached with 3 alkyl groups, and that p lobe is a dumbbell shape, that one lobe lie in one plane and another lobe lie in another plane. So that's what here I just drawn it on the board, that the one lobe is on right side, another lobe is on left side. So that p lobe that has got a positive charge. That positive charge may be present on left side one time, or it may be present on left side or right side. 50-50 chances are there for this. Thus, the OH which is going to attack this particular p lobe, it may attach itself on right side, or it may attach itself on left side. So the chances are 50-50, like our crackjack biscuit, 50-50, mita namkeen. So it forms a racemic mixture, tertiary butyl alcohol. A racemic mixture generation takes place, that is 50% of dextrorotatory form is formed and 50% of levorotatory form is formed. This is called racemic mixture formation takes place, and the process generation of racemic mixture from the reaction, and this process is called as racemization. So the stereochemistry involved in this SN1 reaction is racemization. Racemization is a process wherein there is a mixture, racemic mixture formation takes place. Racemic mixture means 50% of dextrorotatory and 50% of levorotatory form of products are formed, which is called racemic mixture. And the generation of this racemic mixture is, this process is called as racemization. So the stereochemistry of SN1 reaction is racemization. Clear? So coming to the next point, which is reactivity. So in this particular SN1 reaction, the reactivity is the tertiary alkyl halide reacts faster than secondary. Secondary is going to react faster than primary alkyl halide, and this primary is going to react faster than methyl halide. This is what the reactivity involved in case of this SN1 reaction. Tertiary alkyl halide reacts faster than secondary alkyl halide. Secondary alkyl halide reacts faster than primary alkyl halide. Primary alkyl halide reacts faster than methyl halide. This is what the reactivity. Thank you.